So sorry. Oh yeah. So uh so before the GUM, true the academic wanted to know the difference between the true value and the measure value, but after the GUM, a lot of consensus thought that actually, like, we don't know the exact true value of the measurement. Only God knows. So they changed the concept. So they try to understand the distribution of the measurement that the measured value. So instead of just ignoring the true value to understand the true value and the measure value, the difference, just expressing the distribution of the measurement. So as you can, I wrote it that the mathematically is not significantly different from before GUM and after GUM, but the important thing is that the concepts change, so which means that the paradigm shift, and this become the standard. So before that, there was a lot of ways to express uncertainty, but after GUM, the most of the major institution just gathered all and used this one expression. So this is a historical background. And to be more specific, before GUM is like more like the famous scholar is like Laplace or Gauss, and guys like you studied from like high school or undergraduates that like statistics, the central limited theorem or the Lomo distribution or T distribution, and you might hear about like systematic and random error and or like classical statistics. But after the GUM, we kind of made a standard to express uncertainty with measurement uncertainty propagation, combined uncertainty, and we use like coverage factor and not the classical statistics. We use the Bayesian statistics. So it's like the mathematic is a little different, but as you can see in later, it's really similar with before GUM. But I wish you guys know this difference. The concept is changed, and for example, like the so the in Laplace and Gauss, they kind of um establish the fundamental of the statistics. Like you can know that there's like population. If you get the sampling, then you have a sample, and there's kind of like mean. And when you draw the mean distribution, then there's like a Gaussian distribution, which is a normal distribution. And this is kind of like a before GUM. So and also like the famous theorem, like central limit theorem, if there's a lot of different probability distribution, and if you sample them all and make the sample mean distribution, it looks like normal distribution. So this is kind of like a very famous theorem, and this is based on the classical study. And there was one paper. This is the official journal paper that they kind of um, compare the expression of the uncertainty like before GUM and the after GUM. So this is the before and this is after. So you don't have to like understand the whole the equation. Just the important thing is that this is the final uncertainty. And as you can see, there's kind of like BR is kind of like a systematic uncertainty, and the SR is like random uncertainty. This is the expression of the before GUM. So, like after the GUM, we don't say like systematic uncertainty or random uncertainty. We say like uncertainty arising from systematic effect. So there's a kind of like a word difference, and also the the final, or if we just assume that there is no any covariance, which means that all variables are independent, and so that there's no any covariance, then we can express the total uncertainty like this. And so just adding with root mean square, like the systematic uncertainty plus t distribution, and after that like random uncertainty. But after the GUM, you change like expression like this. So we don't multiply the this T is like, as you know, the confidence level. So we don't multiply confidence level at this part. We just totally multiply the coverage vector, so which is a word change to level of confidence. So there's a difference between the how to express the total uncertainty. And this document, the paper says that this GUM method is much more efficient and more consistent to providing the uncertainty interval. And they compared this result with the Monte Carlo simulation, which Jaeon will talk about later. And the Monte Carlo simulation is kind of like a very fundamental method to figuring out the real distribution of the variables. Like we can say this is kind of like a DNS. So if someone says like we analyze the probability variable with the Monte Carlo simulation, it means like we simulated this flow field with DNS. Well, you can say it like that. So they use the method, the Monte Carlo simulation, and they realized that this after GUM method is much more convenient and much more efficient. So after that, the ASME changed the way to express the the uncertainty expression. So when you see the official ASME documents, they kind of distinguish the uncertainties like this, and the official GUM documents distinguish the uncertainty like this. So they only change um, this category. So they are basically talking about the same one. So I'm gonna talk later about what is the type A and the type B, but as you said, like systematic and random is kind of like a systematic is biased effect. So as 편향된 error, 편향된 불확도. So and random is like literally random, so like noise. So I'm gonna talk later about this deeply, and the main point of this historical background is that before the GUM, we wanted to know about the difference between real and the true value and the measured value, but we realized that we can't know any of the true value. So we just changed the concept and we try to understand just the distribution of the measurement, not the true value. So that was the main point of this section. And moving on to the terminology. So you might have heard about the accuracy and the precision a lot when you're studying engineering, and you might think that this could be like a quantity, like qualitatively. Uh, um, so when you say this is 10% accuracy, the accuracy of 10% or 10% accuracy, based on the GUM, based on the concept, accuracy is not a quantitatively it's not able to express in quantitatively. It's just kind of like a basic concept. So I'm gonna talk about like later. So so the point is that in the real field, like engineering, we are still using a lot of terminology. It's mixed. So, but in metrology, the like very famous institutions, they use the words very accurately, and they don't kind of mix the words each other. So the reason why I'm talking about the terminology is that since our engineer field is using a lot of mixed words, I wish you guys to understand the exact meaning of the word and not to confuse. So, and like sometimes like Professor Huang also use a lot of words differently, but I wish you guys know the exact word of the meaning. So, so this was kind of accuracy and precision was kind of like an example of that. So this terminology is all based on this book. So International Vocabulary of Metrology is the official document to explaining about the words. So first of all is the quantity that a quantity in this document we defined a lot of words different with like physics or other fundamental studies. They are just defining the words as they want to understand the uncertainty. So don't confuse with that. So quantity is kind of like a property of the phenomena in body and substance, and the important thing is that they can express as a number So when you say like length or mass or time, you can express as like 5 meter or 10 kilogram or 1 second. So this is all the quantity, and yeah, this is all the quantity. And the next one terminology is like measurement. So I'm not sure you guys ever heard about it, but measurement is a quantity intended to be measured. Like so, if you want, I want to measure a length or time or um, the mass. It's that's the measurement. So the thing that you wanted to measure. So in Korean we call that like 측정량. So this word is very famous. So I wish you guys want to know this. And the second, next one is like measured quantity value. So measurement is not, um, it's kind of like a length time scale. It's not exact the quantity. So if you want to say like 5 kilogram, that it means that the measured quantity value. So there's a little difference between the concept. And as you said, at the front, the measurement uncertainty. So it means that the accuracy of the measurement, but it says like there's a note that the measurement uncertainty is not a quantity and it's not given at the numerical quantity value. So this is not a quantity. You can't express at a numerical value. So this is more like a concept. It's more like a sense. So when you say it has a high accuracy means that you don't know the value, but it feels like it's more accurate. So well, the reason why we say like that is because we don't know the true value. Only God knows. So we can't know exact numbers, but just we can have the feeling. It feels like it's right. So um, it's when you study this methodology, it feels like it's very philosophical. So there's kind of like they kind of have some basic instincts about the uncertainty. They try to express their feelings in the exact words. So yeah, so I wish there's that kind of concept. So measurement accuracy is not a numerical quantity. But on the contrary, the measurement precision is it can express as numerically. This is why the reason it's possible is that precision means that how the closest of the agreement between indication of measured quantity value. So means that you did a lot of experiments, and if they are close together, that means that it has a high precision. So if since you have already numerical values and you can exactly kind of compare with those the values, so that's why you can express numerically. So we use like standard deviation or variance or another kind of like a statistical analysis to express as numerical. So I wish you guys understand like the concept of the accuracy and the precision, so you don't confuse these words. And another one is that I wish you guys know is the maximum permissibility, maximum permissible measurement error. So it's about the extreme value of measurement error. So when you guys buy some like instrument or other device, like when you get the specification, there are some words about like accuracy, and as I said, the accuracy is not numerical. So I wrote it down here that if you have a substitute instrument accuracy in the quantitative term, MP, which is this, is the most appropriate term. So like for example, like if you buy the pressure transmitter, then as you can see, there's kind of like specification. They says like accuracy is how like like 0.5% or like 10%. And based on this GUM, this is the wrong document. You shouldn't say like accuracy. You should say another word. So uh, I asked this kind of stuff to 한국표준연구원. I asked this concept about is this the right word? And the doctor of in that institution told me that this is the wrong, and you have to express as the maximum um, the concept of the MPE. So MPE is kind of like uh, if you measure about like 10 Pascal, then if the measurement, the MP is like 5 Pascal, that means that your measure is between the 5 to 15. So it's like more like a range about the upper and the lower. So, but the terminology is important, so you shouldn't use the accuracy at all in the first place. But since like our field are using a lot of words confusing, so and just you just have to just like understand this accuracy as just MPE. So and this GUM tools have a definition of the uncertainty that this is the official definition of the uncertainty. So that the non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurement. So this means that the uncertainty is basically a parameter and it's non-negative, and it represents the dispersion of the quantity values. So this means that, as I said, we have the measured value and there's a true value. We don't know about it, but we don't know the difference. But we know about the distribution, how the measured value will, like how where the we don't know the where true value is, but we know that true value will be in this circle. So that's the meaning of the uncertainty. So as I told you that historically the uncertainty concept changed after the GUM. Like before that, it was like understanding the error, but after that, it changed to the distribution characteristics. So yeah, this is the definition of the uncertainty. And like it's not important, but the parameter we don't use as like a mathematical parameter. Meaning, we in parameter we define in this GUM, like they said, like it's quantity used to in describing the probability distribution of the random variables. So that's the definition of the parameter. And if you guys are interested, you can read about it. And then how you gonna express this uncertainty, the dispersion of the quantity? How gonna express this? So since we know that we use the standard deviation to express the distribution of the value, so we kind of use that concept, and we use the standard deviation to express the uncertainty. So that's why we use the word standard measurement uncertainty. So uh, the official word of measurement uncertainty in GUM is standard measurement uncertainty. So the reason why we use the standard word is coming from the standard deviation. So I wish you guys know that. And after there's also like coverage probability. It means that it's really similar with the confidence level that you know. But in GUM we use another word, like not confidence in confidence level. We use the level of confidence. So the word is totally different. So when you use the confidence level, means that it's for before GUM. The after the GUM, it's the level of confidence. It's different. So I will talk this more deeply in after. So this was a kind of like a terminology of the uncertainty. So like briefly summary that before the GUM, we wanted to understand the error, but after the GUM, we just give up and we try to understand the distribution of the values, and that the distribution of the values can be expressed at a standard deviation, and that standard deviation, um, yeah, standard deviation. So then there's a lot of source of the uncertainty. Then we should have to categorize and we should have to divide how this uncertainty source, where did it come from? So the GUM tried to understand the difference between the categories. And before that, like this is kind of like a brief uh, slide of talking about the error and the uncertainty. And as I said, error and uncertainty is different. So yeah, this is a basic summary. So uh, there's a lot of way to express uncertainty. As I said, there's a GUM, or we can use just like standard deviation, confidence interval, or using the probabilistic error. But um, in this seminar, we are going to learn how to express the uncertainty with the GUM method. And I want to emphasize, I want to note that the GUM is kind of like one of the methods just expressing the uncertainty. But like as I said, like a lot of worldwide institutions are using this GUM method. So this is kind of like a base, like a standard expression. So well, if you learn this method, that you don't, I think, yeah, you don't have to learn another way to um, express uncertainty if you're not the expert in this field. So, as I said, now we have to understand, like, we have to divide the uncertainty category. Where did it come from? So, this GUM is writing that they evaluated the uncertainty in type A and type B. So the type A is the method of evaluation by the statistical analysis. So when you evaluated the uncertainty with the statistical method, then we call that a type A evaluation. And if you didn't use the statistical analysis, like mean other than, like other method, then we all call that just type A, type B. So you can just understand uh, like if you didn't calculate it as a statistical method, then you just have to think like this is a type B evaluation uncertainty. So this GUM divided the uncertainty into two way, and uh, uh, and they kind of note that this type A doesn't mean random and type B doesn't mean systematic. It's because that, as you can see, these categories apply to uncertainty and not substitute for the words random and systematic. So as you like, if you evaluated the uncertainty source with type A evaluation, that doesn't mean that it's random. Like it's just you just evaluate it at this type A method. So you shouldn't kind of confuse these two. So it says that yeah. So I will just show you the shit. Yeah. I will just show you the schematic that, as I said, like if you use the statistical method to evaluate the uncertainty, even though you use the statistical method, it could be like systematic and random. So the type A doesn't mean the random effect or bias effect. It's just a type A. So you shouldn't be confused with these words. And also at the ASME, they also divide the uncertainty as a systematic uncertainty. But inside that, there are also the type A and type B. So like um, sometimes like Professor Huang says like type A is random effect, but mostly, yeah, that's right. Because mostly you have to deal the random effect with the statistical analysis. But technically, the type A is not only random effect. There are also bias effects. So I wish you don't confuse this concept. So that is why they kind of wrote the word that there's like some publication uncertainty components are categorized as random and systematic, but that doesn't mean that type A is systematic or random. They have both. So they kind of like note that very a lot of times in GUM documents. So yeah, we can just yeah. Then how could you just like then technically, how could you express the standard uncertainty in type A? So, as I said, we use the standard deviation to express the standard uncertainty. And since type A is using a statistical analysis, so as you guys know that we use the very like standard deviation using this equation that uh, 표준 편차. So 표본의 표준 편차. So we are using that, and so by this we express this type A standard uncertainty. And then type B. How could you express the type B evaluation of standard uncertainty? This is kind of that we don't use a statistical analysis. So this has not been obtained from the repeat observation. This is kind of like based on the previous measurement data or manufacturer specification or other calibration or certificate. So for example, like um, if you have a device instrument and you have this kind of like a pressure transmitter and it says like there's accuracy about like 0.5 or 1%. If we understand this accuracy as a word as standard deviation or type B evaluation, then standard if we understand this as a standard uncertainty, then if you measure something like about like 10 Pascal, then the uncertainty is about like 0.5%, which means that you evaluated the standard uncertainty with type B, not type A, because you didn't do any statistical analysis. You don't know how this came from, so you just have to think at this as a type B, not type A. So the reason why we're categorizing this type A, type B is because after like we're going to talk about the total uncertainty, you have to combine this all together. And Professor Huang really likes it. So you don't, like he doesn't like only using a statistical analysis. You have to use all the different sources and you have to combine it all. So, and yeah, he's really, really, um, if you get wrong with this, you can't go further with your journal paper. So yeah, so I want to emphasize that. So when we like understand the probability distribution, there's a very famous Gaussian distribution, but without that there are also very famous distribution like rectangular probability distribution. It's literally rectangular, and this is the triangle probability, and this two length is same. So this is 이등변 삼각형. So this two probability distribution is the famous distribution that we use in type B. So for example, like I will talk deeply left after, but like for example, when you use spatial resolution or temporal resolution, you have to assume this kind of like a probability distribution. So I'm gonna talk later. So we talk about the uncertainty. How can we evaluate? How could divide the uncertainty into categories? And we talk about like the standard uncertainty is based on the standard deviation. So after that, then since there's a lot of sources, you have to combine it together, and I will talk about it. So the process of evaluating uncertainty by GUM framework is the plot is like this, and the flow work is like this. And so first, model the measurements. So there's kind of like a measurement that you want to know, and there's a lot of sources, and there's a variables, and this U is kind of like the standard uncertainty of the X1, and in this X1, there's also a lot of sources. I will talk to you about like example later. And if you like identify the uncertainty sources, then you can evaluate the standard uncertainty, and with the like you can use it as a statistical analysis, or you can use the just certificates of the specification. So you can just divide, you have to divide in two categories, and after that, if you evaluated the standard uncertainty all, then you have to combine them all together with using the sensitivity coefficient, which means that each sources has different weighting. So you have to consider that there are different weighting between variables. So you have to consider that. Then after that, you multiply K, which is called as coverage factor. And in the before GUM, we called this as a confidence level. But in this GUM framework, we say that level of confidence or the coverage factor. So using multiplying this, now you're obtaining the extent uncertainty, or other words like overall uncertainty. So this is the basic framework to obtain the final uncertainty. So I will talk step by step. So first, like since you did an experiment, there will be a value that you wanted to get. So that's why, and there's a lot of variable which will affect to your output, the results. So that will be like x1 to xn. Then To obtain the final conclusion result, you have to kind of like have other values like temporal resolution or spatial resolution. You have to have own values. So that's gonna be like x1, x2, x like xn. Then you evaluate it into type A and type B. So this is the way to understand. It's really depends on what kind of system you're using. So I'm gonna break it down very deeply at after like slides in terms of the PIV. So in like journal paper, there's like a fishbone diagram. It's famous diagram to show the uncertainty source. So like for example, like the what do you call it? Effective density of the particles. If you think like that, then there will be like temperature, repeatability, or the temperature. So as I said, there's only if there's one variable that like particles or like density, then this density also affected by other sources. So y is affected by this, and also x1 is affected by others. So there's kind of like a inside there are another sources inside, so you have to consider all. So this is kind of like a visualization of that. So if you guys identify all those uncertainty sources, and if you obtain this standard uncertainty with the statistical analysis or other method, then now you have to combine them. So combining them is kind of like using the also probability statistics theory. So uh, if there's a lot of like n variables in the system, then you can make the final combined uncertainty, like considering the all values, all variables. Then we can write like this, and the detail proof of this. You can see at the GUM documents, it shows like there are various long equations, and they show that the final conclusion is like this. So as you can see at the behind the second term, there is kind of like covariance that two variable also each variable also have a relationship. So they kind of give they are coupled together, so they give you an like they give you effect each other. So you have to also consider this, but mostly, so we call this as a correlation coefficient, but mostly we don't consider this. We just think as independent. So we just think like this. We just eliminate or just ignore the second term because it's so complicated. So we're not getting a PhD degree of the uncertainty, so we don't have to consider unless it's really important. So mostly that we are doing it in our lab, we don't consider this term. We just consider this because this is much more bigger than this term. So we conclude that our combined standard uncertainty is like this. So if we obtain the combined uncertainty, then now you have to multiply the coverage vector. That, as I said, like this is the reason why we multiply the coverage vector is really similar with the confidence level. So as I it's in the Gaussian distribution, if you want to have the 90%, 95% of the Gaussian distribution, then you have to multiply that 1.96 coverage vector. And if you want to have a 99, then you have to multiply 3, or if you're on a 9%, then 1.6. So, but mostly like we use like 95% level of confidence, and we don't use like 1.96. We usually use just 2 to be simple. So mostly when you read the journal paper, they say just like they multiply 2 or constant 2 or coverage factor 2. So the meaning of the multiplying coverage factor 2 is that they are estimating the standard deviation, the Gaussian distribution of 95%. And at this box, as I said, the level of confidence and the confidence level is totally different. And in GUM, they are also talking about like the term confidence level is not used in connection with that interval, but rather the term of level of confidence. So they are also emphasizing that it's different because if you're going to use the confidence level, you shouldn't consider type B evaluated uncertainty, standard uncertainty. So if you're using just confidence level, the word, that means that your all sources are evaluated as type A with statistical analysis. So, but since we consider the type B for like the famous one is like a spatial resolution. So, since we're considering that, we shouldn't say confidence level. We should say level of confidence. But well, like professor loves confidence level this word. So yeah, but I wish you guys know the concepts between difference between them. And yeah, as I told you, the before GUM they kind of multiplied this uh, confidence level at this random uncertainty. So, but in now after the GUM, we multiply the whole after the combining the uncertainty, including the systematic and the random. So this is a difference. So this is the visualization of the difference. And if uh, I think mostly you will know about the degree of freedom, and especially when you estimate the standard deviation of the sampling, then if there's a over, if we have a sample of 10 samples, over the 10 samples, then we can use the normal distribution. Like uh, statistics says that if you have more than 10 samples, then their distribution could be normal distribution, but like we can estimate their population as the normal distribution, but under the 10, we have to consider as the t distribution. So when we consider the t distribution, the coverage factor is a little different. So when we use the normal distribution, the level of confidence of 95% is 1.96, but before the 10 samplings, then each 95% of the coverage factor changes. So as you said, like when you have like 6 samples, then you have to use the 2.45 coverage factor, or you have more, then you can use like other values. So this is why you have to at least have more than five or more than three of the samplings. Because, like, as you see that if you have only 3 samples, then the coverage factors increase really steeply. So if you want to be really low, because that if the coverage factor since the coverage factor makes the uncertainty bigger, so you should make the coverage factor lower and lower. So if you have a lot of samples, then you can just use this, or yeah, you have to have at least more samples to have a very low uncertainty. So this is a difference. This is the key concept of the sampling numbers. And so this is the basic equation of when you obtain the combined uncertainty. So, like if you did an experiment and each variables are just added together, then you can have the combined uncertainty like this. So you can just like square and add it in, and so this is the absolute uncertainty. But if you have mostly our in lab that we are doing experiments is expressed like this. So sources are all multiplied. So if you want to express the uncertainty, considering this all 3 values, then it's more easy to use the relative uncertainty. If you wanna calculate the absolute uncertainty, you have to kind of multiply y together, and you have to also consider a lot of other stuff. So just if your variables are outcome of the multiply, just use the relative uncertainty. If your outcome is your variable is outcome from the added, then you can just use the absolute uncertainty. So I wish you guys understand this. And if this is the power law, the same, you can just multiply n. So this is a basic uncertainty propagation of if you have a multiplication or the add. So yeah. So coming back, that this is the final kind of like framework. So summarize. So if you have a system, you have to consider the all variables, and in that variables, probability variable, there are also other sources. But after identifying the uncertainty, then you have to evaluate the standard uncertainty with type A, type B, and after that, you have to combine. So, but you don't have to consider the relationship between two variables, each variable. So you just have to just consider this, um, the main term. So we can just root mean square it. And after that, you multiply the coverage factor, mostly two. That is the probability distribution, 95%. So this is, if you earn this extended uncertainty, that means that you is finished with obtaining the uncertainty. So, yeah, that's the kind of like a framework. And I'm going to talk about the exercise, real exercise, how to obtain the real uncertainty. But before that, I will just briefly talk about the significant figures. Significant figure is kind of like a degree. I mean, 유수자 in Korean, and I assume like some colleagues will probably have experience about talking Professor Huang about Yusja a lot, because he's really, really sensitive to this. So if you show kind of like a table or the numbers, like, for example, like if you show the table like this, like value is like 123.56, and like, then he will be super mad because like, can you exactly measure this kind of number? So the 유효숫자, it means that how could you like uh, how could you like expressing your values? You should use only like a few numbers, not all numbers, because we can reliable to that all numbers. So for example, like but in the GUM, they kind of emphasize that two digits are enough to show the 유수자, significant figures. So if you don't know how to express significant figures, you just have to use like two or three numbers. That's kind of like a common sense. And this GUM also told like that. So uh, you shouldn't show numbers to professor like this. You have to change it. So yeah. Uh, Okay, this is kind of like a brief tip. And oh yeah, and also I told you that there's a difference between standard error and standard deviation, and I'll talk about it. First, that standard deviation is um, 표준 편차 in Korean. Yeah, standard deviation is 표준 편차. So there's kind of like a, if we have a sample, there's a population 모집단. There's population, and you sample some values, or like measure something, then you will have sample, and there will be a lot of other values, and between the uh, um, analyzing the distribution of this sample is standard deviation. So if you kind of like measure the pressure 10 times and you obtain the standard deviation, that's this. But the but when you have three set of 10 measured pressure, that means that you have this three samples, and if you obtain each sample mean 평균, and you obtain the mean population, then you guys have the standard error. We call that a standard error, or like we briefly call this SEM. And as this says, like standard deviation of the mean is called a standard error. So this visualize that if you have one sample, this distribution looks like this, and in the center, this is the standard deviation. And if you have four samples, each sample will have each distribution, and each distribution have each mean, and with this mean, you can evaluate the population of the standard deviation. So we call that standard error. So 어, 이 I will talk in Korean, like briefly, like 이게 좀 한국 이렇게 좀 헷갈릴 수가 있는데 이게 아마 고등학교 때 통계학을 배우면서 배웠던 사항일 텐데 여러분들이 이제 모집단에서 10개의 표본을 뽑았을 때 거기서의 표준 편차와 이제 우리가 표준 편차를 구한 거는 그 집단에서 그 샘플 집단에서의 그냥 표준 편차를 구한 거고 실제로는 이제 우리가 추정을 한다고 표현하죠. 그러니까 그 모집단에서의 평균이 어떻게 되는지를 알기 위해서 표본들을 뽑아낸 거기 때문에 그 표본 그러니까 10개가 담긴 표본 3개를 가져와 가지고 그 3개 바탕으로 해서 표본 평균의 표본 평균의 표준 편차. 아마 그 통계학 시간에 배웠을 텐데 이제 그거는 모집단의 평균을 구하려고 하는 거고 이제 모집단의 평균을 구하는 거는 표본 오차고 이거는 이제 그냥 표본에 있는 애들의 디스트리뷰션을 구하는 건 이제 표준 편차다. 그래서 어, 네, 그렇습니다. 그래서 이게 그렇고요. 그래서 이제 우리가 우리가 궁극적으로 구하려고 하는 거는 우리 샘플들의 디스트리뷰션일 수도 있지만 우리가 궁극적으로 구하려고 했던 어떤 모집단의 평균도 구하려고 하기 때문에 이거는 이제 구하는 방식에 따라서 내가 뭘 구하려고 하는지에 따라서 표현 방식이 달라진다. 라는 거를 이제 말씀을 드릴 텐데 이제 그 뒤에서 좀 자세하게 설명을 드릴 거고요. So I wish you know that the standard deviation and the standard error is different. And if you want to know about very detailed information, you can look it up this paper. This is published from the Nature, and they are comparing the standard deviation and the standard error and the confidence interval. The confidence interval is multiplying to 90%, 95%, the constant 2. So the standard deviation and this confidence interval is difference about like twice and the standard error. So this paper is showing that a lot of researchers are using like standard deviation or standard error or confidence interval to show their experiment values. But um, what is most accurate and what is like kind of like a manipulation of the data. So this paper is talking about that. So if you are interested, you can look it up. Yeah. So now we're going to talk about the exact exercise. So because this concept is a little bit very confusing, so I wish you guys to understand very simply. So I will show you the exact exercise. Oh yeah, but before that, like as I said, to not type B, like not type A, like type B, how could you estimate the type B? So if you have like one of the example is that if you have the calibration certificate, which is given by the COLAS, this is the national institution that when you give them a device, can you check my device bias uncertainty or the type B uncertainty? Then they will just do a lot of experiment and do a lot of stuff, and they will show this measurement uncertainty is what they will show you the certificate. So this when they are estimating the measurement uncertainty, they do a lot of like experiment and also they do a lot of repeatability experiment. So which means that they are using the statistical analysis. But since this is a certificate and they just giving you the numbers, the final measured uncertainty, so you don't exactly know how they did it. So that means that this certificate is just showing the type B. So if you give your device to this guys and they give you a certificate and it just says like your measurement uncertainty ruler is about the 0.07 millimeters. So then you just have to accept that. Okay, my ruler has uncertainty about 0.07. So this you just have to think this as just like a bias, not a random. Just like oh, my device has it's starting from this value, and if you do another experiment a lot, and there will be a standard deviation, and you should combine your experiment results and this results together to make the overall uncertainty. So this is the one example of type B. Yeah, and so this is so when you make when you kind of evaluate or show your final uncertainty, mostly you make like this kind of like table. We call that uncertainty budget table. So we show, I'm sorry to show this in Korean, but I will tell you in English. But this is like uncertainty source, and this is a type, and this is the standard uncertainty, and this is like sensitivity coefficient, and this is a distribution, and this is divisor, which is correlated with this probability distribution, and this is a degree of freedom. So if you wrote it down all the sources and you combined it and you multiply the coverage factor, and you have the overall uncertainty. So if you want to show that how's your system, how's your measurement uncertainty, then you have to show this budget table. That's the most exact and very um, yeah, exact answer of the question. So, and also this only shows like the sources, but as I said, there's a sources and there's also sources in sources. So each sources also are affected to others. So they are like kind of like inside. So you have to understand that. So you have to understand what variables and what kind of properties are influence or affecting my uncertainty values. So you have to know that. Okay, so this is the exact exercise of how to calculate the standard uncertainty. So I assume in three categories, three situations. Like for you, you have voltmeters and you want to measure the voltage, and you have nothing, you just have just voltmeter. That's one case one. And but you have kind of like a certification that the manufacturer gave you, and there's also like, even though you have specification, you give your this voltmeter to Colas, the National Institute, and they give you a calibration certificate. In that case, how should you express your uncertainty? So in this, each case has different values. So which means that, well, based on your information, the final uncertainty values is changes. So you don't have to like worry about, does my uncertainty calculation is right? You don't have to worry about it, because you just have to do try your best to calculate the uncertainty. So because, as I said, we don't know the true value. We don't know any about like real distribution. So the thing that we could do is trying best to estimate the uncertainty. So okay, the first one. So if you have nothing, you don't have any specification or any other calibration certificate. So you did 5 experiments, and so it's like x1, x2, x3, x4, x5. So you have 5 voltages, and normally we are using the digital voltage, a voltmeter. So this voltmeter has a resolution about a zero point 0.5 voltage. So which means that this voltmeter can express zero point 0.001 voltage. They just will round off, or 뭐 반올림하거나 아니면 내림하거나, they will do like that. Um, so you have to consider the sources is that since you did 5 experiments, which means that repeatability is affecting on your results, which means that it's like a noise or something. And since you're using there's the resolution has a limit, so you have to also consider also that. So there's 2 sources, resolution and repeatability, and the resolution is type B, because this is we didn't analysis this as statistical. We know that that is kind of like a basic function of this voltmeter. So we don't have to analysis this as statistical method, which means that we don't have to do a lot of repeat. So this is type B, and the repeatability is type A. So as I said, like this resolution is 0.01, and we are dividing at 2 root 3. I'll talk to you later. And this since we did 5 experiments, so we have to consider the t-distribution. As I said, if more than sample is more than is lower than 10, we have to use the t-distribution. If we have more than 10, we have more than 10, we have to consider normal distribution. So since we did only about 5 experiments, so we have to use the t-distribution. And as I said, like if you're considering yeah, we did a 5, so then we have to divide it to 5 root 5. And the reason why we are dividing this zero point zero 0.01 to this divisor, we call this a divisor. The reason is that um 잠시만요. Shit. Okay. The reason why we are doing this is, yeah, I told you that we have to, when we evaluate the type B standard uncertainty, we have to think about this two famous distribution. Which means that if the voltage is not showing, or if that voltmeter can show zero point zero 0.01 voltage, which means that there's a discrete between two zero point zero 0.01 voltage, and which means that true value could be anywhere in this distribution. So which means that we have to just consider as rectangular. So we can like this we can assume as a normal distribution, but it's not kind of like common sense because we don't know any information. So we just assume that every voltage could be in this distribution. So we just consider as the rectangular and the rectangular of distribution. This rectangular distribution has a standard deviation as root 2 3. So this is why we divide at root 3, and the total is 2 root, this is the, yeah. So that is why we have to divide into half. So we consume that the true value could be inside in this rectangular distribution. So we use this divisor to obtain the standard uncertainty and using the repeatability. So using combining these two uncertainty sources, you can use like this equation. And as I said, we use the coverage factor 2 normally to obtain the level of confidence about 95%. So this is the final uncertainty of this measurement. So yeah, this is all. And next is that, yeah, next is that when you have a specification, so what it happens, the first one is that if the spec sheet accuracy says like 10%, the reason why I write it down as accuracy is that most of specification talks like accuracy, but as I said, this is not accurate word, but I just wanted to show that most of the specifications wrote like that. So specification 10% and absence of calibration certificate, and you did 5 experiments. So then how could we now obtain our overall uncertainty? Is that we assume that accuracy means that the MPI, the total the extreme value, the upper and the lower limit, so it has 10%, and in the absence of the calibration certificate, you just have to assume this is a 10%, and this 10% could be just rectangular probability distribution. So just assume like that, and which means that you have a bias, which means that the accuracy 10% means that you measure something, that there's a difference between true values, not true value, but like there's an uncertainty between 10%. So you just assume this has a bias, and you did 5 experiments. So you have bias and repeatability, and if you want to obtain the standard uncertainty of this bias, use the representative value. So you use as this mean of this 5 results and multiply with 0.1 because this is 10%, and divide as a root 3 is because it's rectangular. So this is how we obtain this bias. And after that, since you did it a 5 measurements, so you have to do also this repeatability analysis. And after that, just combine this together, and after multiplying coverage factor, you can have 95% overall uncertainty. And you might think like wonder like where's the resolution? So where's the why didn't you consider the resolution? But the reason why we didn't consider the resolution is that we already considered at this accuracy. So we think that there's a 10% minimum and maximum difference, and buying that, there are also it already included that in our analysis. So if you are interested about this, you can read this paper, like effecting of the rounding on the moment of probability distribution. So this means that if you earn the standard uncertainty, then the bias the what do you call it? Like the resolution is already included in this results. So are you interested? You can look it up. And the last one is that if you have a calibration certificate, so as I said, like we have a specification, it says like accuracy is 10%, but oh, sorry, it's not absent. If you have the calibration certificate, then you don't have to consider like this accuracy because this is now meaningless. This official document is much more, it's literally official. So, uh, before the experiment, if you have calibration certificate, that's the bias. That's the starting point, and you don't have to consider all other stuffs. So if you have the certificate, then you just have to consider the calibration certificate, and you don't have to consider anything. Just use the number that they give, and the same thing repeatability. And so the overall uncertainty could be like this. So the uncertainty changes when the information changes. So, um, as I said, like there's no any exact or like perfect calculation of the uncertainty. It changes as the information, or you can it depends on the system. So you don't have to worry about it. You just have to try best to understand and calculate the uncertainty. So yeah. And also, like for example, like from pressure transmitter. So you have your specification. You can calculate like this. So uh, so the next one is, now we talked about the voltmeter. Is voltmeter is kind of like a single measurement system. Just you just have to just uh, you just have to check the measure the voltage. So it's very simple, but honestly, like in our lab or that the experiment that we are doing is not that simple. We have a lot of procedures and a lot of process, so they have a lot of sources. So we can't think that simple. So each measurement system has very complicated sources, but in terms of PIV, since we are our lab or using a lot of PIV experiment, so I will show you how to calculate the PIV uncertainty. So the first one is that you make a system setup. So that's a physical setup. So this is there's a kind of like a error source. For example, like if you didn't make this camera and the wind tunnel perpendicularly, there will be of course there will be an error source. And well, like laser, if laser is tilted, then there will be also a sources. So um, but unfortunately, as you know, we can't track that physical uncertainty because we don't know how much tilt, or how much, uh, well, like for example, like laser, if the laser is weird, like the radiation profile is not that good, then we have to also consider that. But we just assume that our measurement setup is perfect. So, well, because this could not be this could not be accurate, but most of the PIV um, studies just assume that their measurement setup is perpendicular and every setup device is perfect. So they don't actually consider about this physical configuration. But if you're studying at like very deep PIV uncertainty, yeah, also you have to consider that. But since we're not doing that, we're researching other stuff, not like PIV uncertainty itself. So we just assume there's no any error source in this physical configuration. But yeah, and after that, if we get the particle image, and this particle image we combine like we integrate together and do cross correlation, we obtain the particle displacement with vector, and we obtain this particle velocity. So each has this is a image process, and this is kind of like a multiplying source, multiplying the factors, and there are also the air source. So you have to consider this too. So I'm gonna elaborate how to obtain this two sources. So the characteristic of the system is that you don't have any calibration certificate. You can't give this all setup to the National Institute. That doesn't make sense. So we don't have any calibration certificate, and uh, and there's no any like actual specification shit. So manufacturer doesn't give you any like uh of the specification of this system. We just have to combine this all. So we don't have any official documents or data sheet. So this the reason why it's very difficult is that we made this integrated system like DIY. So if someone made it and if there's kind of like expert and uncertainty, they could give you a number. But since we're doing in graduate school, there's no any that kind of stuff. So we have to understand by ourselves. Uh, and before showing the budget table, I want to explain about the ensemble of the PIV. Um, 잠깐만. 한국말로 잠깐 설명하면은 이거 약간 인턴분들은 잘 모를 수도 있을 것 같아가지고 그 PIV라는 게 그 약자가 파티클 이미지 벨로시미티라고 해가지고 입자를 이용해서 속도를 계측하는 방법 중에 하나인데 이제 그거 같은 경우에는 지금 보시는 것처럼 카메라와 이제 레이저를 수직으로 둬가지고 충동해서 이제 파티클을 불면은 그 파티클이 이제 레이저를 맞고 발광이랑, 그러니까 산란을 하게 되면서 그 산란 빛을 카메라가 계측을 하게 되고 그 보이는 것처럼 이런 식으로 이제 파티클이 지나가는 모습을 카메라로 찍은 거고 그 카메라를 이제 두 방 연속으로 빠르게 찍게 되면은 이런 식으로 이미지 두 개가 나오게 되고 그 이미지를 이런 식으로 사각형으로 잘게 쪼개가지고 일종의 약간 픽셀처럼 잘게 쪼개서 이 각각의 이 서로 매칭되는 이 지점을 서로 크로스 콜리데이션이라고 표현하는데 그냥 이제 일종의 그냥 포개가지고 얼마큼 얘네들이 평균적으로 여기로 이동을 했는가. 왜냐하면 굉장히 짧은 시간 안에 카메라로 이미지를 찍기 때문에 입자들이 순간적으로 살짝 움직이게 되고 그 살짝 움직인 정도를 이제 벡터로 표현을 하게 되면은 여기서 있던 입자들이 여기서 얼마큼 이동했는가를 평균적으로 이제 우리가 그 수치화가 가능하고 그 수치화 바탕으로 하면은 이건 이제 그 디스플레이스먼트 벡터니까 그걸 차원을 이제 속도로 맞춰줘야 돼가지고 우리가 시간을 알고 있고 그 거리를 알고 있기 때문에 이제 이제 속도를 구할 수 있게 되고 우리가 실제적으로 구한 거는 사실 이 입자가 움직이는 속도를 구한 거긴 하지만 입자 자체가 플로우를 따라간다라고 하는 이제 그것도 이제 판단하는 파라미터가 있는 스톡스 넘버라고 파라미터가 있는데 이제 그 스톡스 넘버가 굉장히 그러니까 그 유동을 잘 따라간다라고 판단이 들면 그냥 이 입자 속도를 유동 속도라고 가정을 하고 이걸 이제 입자 속도로 유동 속도를 계측하는 그게 이제 일반적인 이제 PIV 계측 기법인데 그래서 이제 그거를 지금 설명하고 있는 겁니다. 그래서 저희 연구실에서 이걸 워낙 많이 쓰기 때문에 이걸로 어떤 식으로 이제 언설턴티 계산하는지를 이제 알아야 돼서 이제 그걸 설명을 하고 있고요. 근데 이제 before that, like since this is turbulent, so it's not like uniform flow. They have a lot of fluctuation, and each image pair has one velocity field. So if you want to obtain the mean value, the mean velocity field, you have to consider if you want to calculate the standard uncertainty of the mean velocity field for mean velocity, then you have to consider like ensemble. So since there you are like imaging a lot of picture like a lot of pairs, and if you have like n pairs and you just um make mean, then all mean, then as the image pairs increase, then the mean velocity will converge, and this means that 양상불 converge. And this doesn't show any um, the mean value of standard uncertainty. This means that you have just one data. Yeah. Since you want to know the mean velocity, that means that you obtain just one mean velocity in this image pair. So, which means that if you want to know the uncertainty, then you have to do like at least 3 or 5 experiments, and you have the image set, the total set. So 1 set, 2 set, 3 set, and using this 3 set, you can obtain finally the measurement uncertainty of the mean velocity. So this is the difference between the standard error and standard deviation that I told you before. So, but normally we don't express this mean velocity measurement uncertainty. We just show that our total PIV system has like 5% uncertainty or 10% uncertainty. We don't calculate this much, but if you want to really know the uncertainty concept, then you have to calculate like this. So, 이거 한국말, did you understand? Okay. 그 한국말로 잠깐 설명하자면은 이게 유동 자체가 플럭추에이션을 하기 때문에 날리기 때문에 단순하게 그냥 이미지 하나를 통해 가지고 벨로시티 필드를 딱 뽑아냈다 해가지고 그걸 우리는 이제 평균을 알 수가 없고 시간 평균을 알 수가 없기 때문에 시간 평균을 알기 위해서는 굉장히 많은 시간을 거쳐서 사진을 찍어야 되고 그 사진을 찍었을 때 이제 그 뭐 예를 들면 천장을 찍었다. 그럼 천장을 다 같이 그러니까 앙상블이라는 게 결국 평균인데 이제 앙상블이 이제 물리학에서 온 개념으로 우리가 이제 플럭추에이션 하고 있는 어떤 개가 시스템이 있다 하면은 거기서 대표값을 뽑아내는 방식이 결국에 전체를 다 평균시켜버려가지고 이제 거기서 수렴하는 값을 하나 본다가 이제 앙상블이라는 개념인데 동일하게 이제 이 시스템의 어떤 평균 유동장을 보기 위해서는 이 이미지 페어를 계속 쌓아가면서 수렴하는 하나의 속도에 대해서 봐야 되는 거고 그러면은 이 값이라고 하는 거는 이제 mean velocity라고 하는 거는 결국엔 우리가 천장을 썼지만 결국엔 하나의 값만 도달을 한 거지. 그래서 아까 얘기했었던 이제 표본 평균이 하나의 데이터 값이 되는 거기 때문에 그러니까 우리가 이제 mean velocity의 불확도가 얼마큼 되냐라고 물어보면 이 천장에서의 그 스탠다드 디비에이션을 구하게 되면은 잘못된 계산값이라는 거를 지금 설명하고 있는 거라서 천장을 이제 찍어가지고 걔네들의 뭔가 분포를 보게 되면 그냥 하나만 이렇게 나오게 되고 이 얘네들의 이제 스탠다드 디비에이션을 구하게 되면은 그거는 이제 터뷸런스 인텐시티가 되는 그러니까 터뷸런스 인텐시티라고 하는 거는 플럭추에이션 하는 정도를 나타내는 게 터뷸런스 인텐시티이기 때문에 이거가 이제 우리가 이제 여기서의 스탠다드 디비에이션은 이제 민의 스탠다드 디비에이션이 아니고 그냥 우리가 본 유동장의 스탠다드 디비에이션이기 때문에 플럭추에이션 하는 정도만 본 거고 우리가 보려고 하는 거는 민 벨로시티가 얼마큼 흔들리고 있느냐, 언서턴티가 얼마큼 되냐라는 거기 때문에 우리가 갖고 있어야 되는 거는 민 벨로시티 데이터들이 있어야 되는 거지. 그래서 민 벨로시티 데이터들을 얻으려면 천장을 3번 찍어야 되는 거지. 3번 찍어서 3개의 데이터 셋이 있으면 이 3개로 이제 민을 추정을 해가지고 아까 얘기했었던 이제 표본 오차를 이용을 하게 되면 이제 그 민 벨로시티의 그 언서턴티를 알게 되는. 근데 이제 얘기했던 게 이 정도까지를 나타내지는 않아서 워낙 이제 데이터도 엄청 많아야 되고 뭐 계산도 엄청 해야 되고 사실 지금 그 이미지 페어 뭐 천장 해가지고 민벨로시티 하나 뜬다 했지만 이게 전체 2000 바이 2000에서 벡터가 2000 곱하기 2000개가 나오는데 그거를 다 계산해서 각 지표별로 각 그 픽셀별로 벨로시티 민을 뽑아낸다는 게 계산량이 어마무시하기 때문에 사실 그렇게 나타내지는 않고 그냥 개념적으로는 이렇다. 그래서 만약에 여러분들이 진짜 이 뭔가 민을 정말 구체적으로 구해야 되는 거라 하면은 이렇게 계산을 해서 언설턴티 구하면 된다라는 거를 이제 설명을 드리고 있는 거고. So yeah. So when you're using like PIV, there's a lot of image pairs. So like different with multimeters, we have sets, we have pairs, and we have like each image. So that's like kind of different between multimeter and this PIV system. But we don't actually use like literally show this in paper. We just do this uncertainty analysis. So if like if you conducted the 5 sets of 10 experiments, then how could you show the uncertainty budget table? I'll show you at this slide. So the assumption is that you conducted 5 sets of 10 experiments and you have each mean velocity. And it says like the assumption is that you have every 10 measurements is converged, and that each 5 ensemble data has the magnification and timing harbor and PIV uncertainty. So I will explain about it. As I said, like if you want to obtain the PIV particle velocity, then you have to use displacement vector and multiplying the magnification factor. And after that, you have to divide into the spatial temporal resolution that you're using the time interval between the image. So that is the equation. Then, as I said, like if this is all multiplied, so that means that if you wanna, you don't have if the all oh, if the variable is all multiplied, then as I said, it's easier to do just use this, not this one. So you don't have to understand the absolute uncertainty. You just have to know about like relative uncertainty. So you can just divide each variable into the standard uncertainty. So this is more easier to obtain and calculate. So I'm gonna show that. Oh yeah. So this delta means that is percentage, not the absolute. So you can understand like that. And this is also like this is the Professor Hyungmin Park, the lab journal paper. They also use like this, like magnification factor and displacement and the time interval. So mostly like when you explain about your measurement uncertainty in your system, you just use about like one paragraph or like two paragraph. Like if you're not the if your paper is not about subject is not about the measurement uncertainty, you don't have to actually like wrote a lot about explaining about the uncertainty. So this is kind of I show this paragraph because wish you guys have some of the feeling about how long I should wrote. So it could be weird that it's really complicated concept, but you only just show one or two paragraphs. This could be a little bit sad, but well, if you want to write properly, you should know the concept. So this is the final like overall of PIV uncertainty. So as I said, we just only consider about like three component like sources, not about like physical configuration or other like ensemble, and also we don't consider about vector. Like as you said, um, as you can see, like we are thinking about um, Scholar, which means that um, um, like each pixel has each own vectors, and even though there are velocities same, the direction could be different. So which means that we are not considering the direction of the uncertainty. We just consider about Scholar. So the magnitude. So you can uh, if you ask why you don't consider about direction, I could say like because nobody consider that right now because it's super complicated and that's not the subject of our paper. So we just like roughly or just do our best in terms of our lab experiment. So this is the standard. We just consider only three component sources. So magnification factor, and if magnification factor means that you have to change to the pixel to meter, so we use the ruler a lot. So a ruler also has a resolution. So we have to consider that. I will explain how to calculate this pixel resolution divided to root 6. And this U delta t, this temporal resolution, the timing curve, and the image between the time interval is we consider as a rectangular, so we divide it to 2 root 2 3 as I explained at the voltmeter. So, and also the displacement vector, I only wrote it down as a 0.1 pixel, is because if you want to obtain this displacement vector standard uncertainty, you have to do a lot of like simulation, especially like Monte Carlo simulation. So it's very complicated. Um, it's very complicated to obtain the standard uncertainty of displacement vector because we are using the like PIV software program. So it is well known that in academic society, like PIV, if the Stokes number is really good, then you just have to consider it as zero point 0.1 pixel. So it's like 국룰. So yeah, so you just have to use zero point 0.1 pixel. And combining this together, as I said, there's no any type A because normally when you do PIV experiment, we don't do a lot. Like we don't do like 5, 6, 7, 8. Like so, as I said, if you want to show this, you can do that. But most of the paper doesn't consider about repeatability. So you can just do one experiment, like 1,000 pairs or like 2,000 pairs, and that's it. So you don't have to do a lot of sets. But if you want to be more accurate, you can plus type A and include that your repeatability is very good. But mostly nobody do like that. So, uh, yeah, nobody do like that normally. So the basically like you only have to consider this three sources and you combine it like this. As I said, this is a relative. So you if when you're dividing this like absolute value, well, magnification factor and delta t and mean, um, you have to use the representative value, which means that it's mean. So since you have 1,000 pairs, which means that you have 1,000 time intervals. Like, of course, you set set the time interval as 10 microsecond, but it doesn't mean like literally like 10 microseconds. But um, you have to use the mean. But if you're not measuring the time interval, then you just have to use a 10 microsecond. So the value that you want to put in this should be the representative value that you set, the number that you set, or you measured, and you have the mean value of it. Then you can just put the mean value. So that's why we use this displacement vector as a mean. So when you have one pair of the velocity field, then there will be like 1,000 of vectors, and there will be a ton of displacement vectors. So then how could you show the uncertainty? Which means that this all vectors has all their own uncertainty, but you cannot show like 1,000 uncertainty values in paper. So you have to show the representative of uncertainty value, which means that you just mean them all and show the mean displacement vector, mean displacement value. So you have to put that in and multiplying 2, then you can have the overall relative uncertainty final. So that's the reason. And 이거 방금 이해했는지 모르겠는데 이 각각의 이제 상대 불확도를 구할 때 넣어줘야 되는 이 밸류들이 만약에 예를 들면 내가 시간 차를 10마이크로세컨드로 넣었다라고 하면은 그냥 10마이크로세컨드로 넣으면 되는 거고, 근데 이제 이 디스플레이스먼트 벡터 같은 경우에는 밸류 같은 경우에는 이제 이 이미지 페어에서 1,000개, 뭐 2,000개가 되는 벡터들이 튀어나오게 되는데, 그러면은 그 2,000개 벡터들마다 그 움직인 거리가 다 다를 텐데, 그러면 이 거리가 다 다르고, 그럼 이 값도 다 1,000개씩 나오는데 이 1,000개를 다 보여줄 수는 없으니까 그냥 우리의 어떤 이 PIV 시스템에서 언설턴티가 어느 정도 된다라는 것만 보여주면 되는 거기 때문에 이게 진짜 뭐 언설턴티 논문이 아니라고 하면은, 그러면 그냥 이 전체에서 구한 벨로시티 필드에서 싹 다 그냥 민을 쳐가지고 대표적인 하나의 디스플레이스먼트 밸류만 뽑아내면 된다. 라는 의미로 이제 얘기를 한 거고요. 그래서 그렇게 이해를 하시면 될 것 같고. So, the reason why we use the magnification uncertainty like this is because, I will show you how to evaluate to obtain the magnification uncertainty. So, since we are using the PIB Lab software, so when you obtain the magnification factor in this program, you click this dots, this region, and at the starting point and the ending point, and this software will automatically calculate the distance between these two pixels, and you have to put the real distance that since the ruler has it's departed from about the distance is 10 millimeters, so you have to put 10 millimeters, then this will automatically calculate this magnification factor, that 1 pixel per frame, and that's they calculate the magnification factor, but they don't calculate the uncertainty. Then how could I calculate this uncertainty? Is that we assume this as isosceles triangular, so this distribution. So since, for example, like this is the ruler, is has the line that shows the distance. But since you have to think that we don't know between where this exact distance, so we know that this this line and this line is apart from 10 millimeters, but since the dot could be inside this region, so you have to consider like the minimum of the distance could be like this, and the maximum could be like this. So this, since the spatial resolution is 1 millimeters, which means that the uncertainty has 1 millimeters in the ruler. So you have to consider the distribution of this 1 millimeters, and we have to, since it's symmetric, we can consider as the isosceles triangular. So if this is a isosceles, then we can use the divisor as a root 6, and we can calculate as the standard deviation like this. So the exact calculation is look like this, that since the max and mean, there's a difference, and since this is a relative uncertainty, if you calculate the relative, then it will look like this. So if you want to calculate this relative uncertainty, you can use this equation. So 이거 잠깐만. 제가 영어로 제대로 설명했는지 모르겠는데, 그, 한국말로 설명하면은, 지금 이 바가 그냥 설명하고 있는 것 자체가 이 위치만 하나 설명하고 있는 거기 때문에, 정확히는 이 레졸루션 사이에서는 점이 어디 있는지, 그러니까 정확히 위치를 모른다고 우리가 생각을 해야 되거든요. 왜냐면은, 이 자라는 것 자체는 이 지점에 대해서만 정보를 주고 있는 거기 때문에, 이 사이는 어디에 찍히든 우리는 실제로 잘 모르는 거기 때문에 이 사이에 대해서는 우리가 모른다고 생각을 하고, 그러면 여기도 모르기 때문에 결국에는 이 거리 자체가 시메트릭하게 재질 수밖에 없어서, 그러면 이제 그러니까 그 직사각형 모양이 아닌 이런 식으로 중앙부로 갈수록 좀 더 프로버빌리티가 올라가게 되는 이등변 삼각형을 고려를 해줘야 되고, 이 이등변 삼각형에 의해서 이런 식으로 이제 우리가 계산을 할 수가 있게 된다라고 이제 말씀을 드릴 수가 있을 것 같습니다. 그래서 어 그러니까 이걸 좀 자세히, 그러니까 그러니까 이 픽셀 레솔루션이 이 사이를 얘기하는 게 아니라, 이걸 좀 더 확대를 해보시면 알겠지만 이 선이 굵기가 있거든요. 그러니까 굵기가 있기 때문에 그러니까 이 아래랑 이 위랑 어디가, 예를 들면 여기가 60mm인데 어디가 정확히 60mm인지를 모르기 때문에 눈으로 봤을 때, 그러니까 이 점을 나중에 찍을 때 여기랑 이 살짝 위랑 둘 다 60mm로 생각을 하고, 여기서도 이제 이게 둘 다 50mm라 생각을 하고, 그러니까 이 선에 대한 어떻게 보면 굵기라 생각하면 되는데, 이 굵기에 대해서 우리가 이제 고려를 해줘야 돼가지고, 그래서 우리가 이제 이등변 삼각형으로 해서 이 빈맥스라 하는 거는, 여기서 이제 이 민이랑 이제 맥스를 빼는 거는 이 굵기가 가장 안쪽에 있을 때, 이 선 굵기가 가장 안쪽에 있을 때가 민이고, 이 바깥쪽에 있을 때가 맥스고 해서 이제 그 수 둘을 빼가지고 이제 계산을 하는 거여서 그래서 이제 이게 룰러의 레솔루션이 아니라 이제 픽셀 레솔루션이라 하는 게 이제 픽셀이 이거를 이제 구별을 못한다 이 굵기를 그래서 이제 그 픽셀 레솔루션이라고 제가 이거 위에다 써놓은 거고요. So yeah, I will talk this like privately more deep like because a little bit complicated. So yeah, and finally, that this displacement uncertainty. As I said, the universal uncertainty constant is zero point 0.1 Kungler. So you don't have to think a lot about it if you're not gonna to analyze the uncertainty very deeply. So you just have to use zero point 0.5, a zero point 0.1 pixel. Well, so if someone wants to know about more, then you can just look it up. This reference. This guy is kind of like a very famous scholar about the PIV uncertainty. So you can look it up. And yeah, this is the final budget table of the PIV. So there's magnification factor, and you have your own magnification factor. This is this this one, this magnification factor, and yeah. So 600 nano and the 1.5, you can calculate like this, and you will obtain the final overall PIV uncertainty. So if you want to show the total like this in your paper, you should make like this table, and probably professor will love it. So yeah. Yeah, other lab is not important, but like I kind of search other lab. So like Professor Hyungmin Park, Do, Kim Ho-young, Song Sung-jin, like Haejun Choi. So um, they kind of there's no any kind of consistent. They all use different. They just do whatever they want. So because this is not metrology, we're kind of engineer field, so they don't actually like most professor doesn't it's not very accurate to uncertainty. They just show very roughly. Um, so like as you said, like Song Sung-jin, they show like machinery accuracy specification. As I said, they just show the specification number. They say like accuracy 10%. But I said that's not actually right word. But Song Sung-jin lab just wrote that specification data sheet, and Boyoung Kim use a lot of error bars, and they don't use like uncertainty word. They do. I searched about like 10 years paper, and they never use the uncertainty word. They just use error bars, and um yeah. And also Haeja Choi, uh, maybe you guys someone who is doing the numerical studies. Also CFD, there's also uncertainty field. So we say it like you. UQ, uncertainty quantification. So we say like UQ field. So someone who is interested, you can look it up. There's a lot of journal paper also. So it's a little bit different with the experiment part. So yeah, this is our lab like example. I will give you this slide, this PPT, so you can look it up after and the end of the seminar. Yeah, this is our e-flow, and this is Song Sung-jin. So yeah, this is all. They in this one paper they just show like this. This is uncertainty end. So they don't explain it, they just show it. And well, this is not our professor style. Our professor wants to explain it. So and this is not they didn't measure it. They just look it up well the specification feet shit. So yeah, and like accuracy, they just show the data sheet, which is not actually like a right thing. But and this is Hoyoung Kim. There's a error bars like technically error bars is not right expression. The uncertainty is much more accurate word, but most like nature or science are still using the error bar. So uh, yeah, this is a MRV uncertainty, and actually, I don't know exactly a lot about MRV because this is like type A. This is not about like type A, it's like type B, which means that they evaluated their MRV uncertainty by their own way with their own logic. So in our NAS, there's a MRV uncertainty PPT that Q made. So if you're interested, you can look it up. And this is kind of like a historical development of the MRV uncertainty. So yeah, and so the conclusion is that we talked about the historical background of the GUM. So, as I said, before the GUM, we wanted to understand the error between the true value and the measured, but now we realize that we don't know the true value. So we try to understand the distribution of the measured value, and this is now kind of like a standard expression of a whole major institution, and yeah, and they kind of say that this evaluation uncertainty is not a kind of mathematic procedure. It's kind of like more it's integrity, and we don't know exact value. So as I said, you have to do best, and if you did your best, then that's good. So you don't have to be worried about like if you're wrong or right. So if you considered all the sources that you can, then that's could be the good one. So yeah, that was the important part. So yeah, I think that's end. And I could tell you that if you're interested in learning about uncertainty more deeply, in 한국표준과학연구원, there's kind of like a uncertainty seminar, not seminar like lecture. You can do it $500. So if you want to know it, like you can listen it. So so this is the end of the seminar. Yeah.